Inside a propulsion test chamber, a rocket thruster firing continuously generates temperatures exceeding 2,000 degrees Celsius. At this scale, materials must maintain their precise structural geometry while glowing white-hot. To meet these requirements, engineers rely on the specific vertical column of the periodic table, known as Group 4. This group consists of three naturally occurring metals, titanium, zirconium, and hafnium, along with the synthetic radioactive element rutherfordium. These are silvery refractory metals, defined by their ability to withstand extreme environments and resist chemical degradation across a wide pH range. Their primary engineering metric is a high melting point, which significantly exceeds that of standard structural metals like aluminum or iron. These macroscopic properties are the predictable result of the element's underlying electronic and physical structures. The survival of these metals in aerospace applications is the direct consequence of their specific valence electronic configurations and temperature-dependent crystal lattice mechanics. To understand these thermal limits, we have to look at the foundational atomic structure of a generic Group 4 element. Group 4 elements share a D2S2 valence configuration, with 2s and 2d outer electrons. Sharing these 4 electrons creates a stable +4 oxidation state. Furthermore, d-orbital spatial orientation allows significant overlap between adjacent atoms, creating a remarkably dense, strong bond network. This high cohesive energy is what makes these metals refractory. It requires immense thermal energy to vibrate the atoms enough to break these bonds and melt the material. This same interatomic strength prevents environmental molecules from penetrating the surface at room temperature, providing the group's baseline corrosion resistance. The structural integrity of a rocket component is defined by the binding energy of these 4 microscopic valence electrons. Beyond individual bonds, we must examine how millions of these atoms organize themselves into a macroscopic crystal lattice. At room temperature, Group 4 metals naturally organize into a rigid hexagonal close-packed, or HCP, structure. When the temperature rises to a critical threshold, the material undergoes an allotropic phase transformation. The lattice stretches and reorganizes into a more open body-centered cubic, or BCC, formation. This BCC structure is more open, which makes the metal hyperreactive at high temperatures. In this superheated state, the metal becomes vulnerable to contamination from environmental oxygen, nitrogen, and carbon. These small non-metal atoms invade the lattice, wedging themselves into the empty spaces between the larger metal atoms. This is known as interstitial embrittlement. These impurities act as microscopic obstructions. They prevent the metal atoms from sliding past one another, which is how a metal normally bends without breaking. The result is a loss of ductility. A material that should be flexible becomes brittle, leading to sudden, catastrophic fractures under load. While these metals are champions of heat resistance, their thermal phase shifts introduce vulnerabilities that engineers must actively manage to prevent structural failure. If we move vertically down the group on the periodic table, we can analyze how the physical size of these atoms changes. Generally, as you move down a group, the atomic radius increases as more electron shells are added. This occurs as expected from titanium to zirconium. Atomic radius increases from titanium to zirconium, but at hafnium, growth stops entirely. This lanthanide contraction occurs because 14 F-block elements are inserted. Their electrons provide poor shielding, allowing the nucleus to pull outer shells inward, contracting hafnium's radius to match zirconium's. This identical sizing makes zirconium and hafnium chemically nearly identical, making them notoriously difficult to separate during refining. Despite this chemical similarity, their nuclear properties are opposites. Their different atomic masses and internal structures change how they interact with free neutrons. Zirconium allows neutrons to pass through, making it ideal for nuclear fuel cladding. Hafnium is a powerful neutron absorber, preferred for control rods. The lanthanide contraction creates a specific chemical pairing, where 2 nearly identical metals must be used for entirely different roles in nuclear engineering. There is a direct causal relationship between these atomic electronic structures and the macroscopic performance of these metals in the field. The D2S2 configuration and the transition between HCP and BCC lattices dictate how titanium performs in high-stress aerospace components. The lanthanide contraction explains why zirconium and hafnium are inseparable in nature, but functionally distinct in nuclear reactors. Rutherfordium completes the group as a synthetic extreme, existing for only seconds before its radioactive nucleus decays. Strong metallic bonding, driven by d orbital overlap, yields high melting points. Lattice reorganization under heat creates the risk of interstitial embrittlement. Poor shielding in the F block dictates the materials used to manage nuclear fission. By understanding the electronic and crystallographic rules of Group 4, engineers can predict and manipulate how these materials will behave in the most demanding environments on Earth.